Hey everyone, welcome to another episode of Let's Lead. Today we'll be talking about activation functions in deep learning, basically, right? It's used in mostly in deep learning. Now let's get started. So the very first question is, what are activation functions? Right? What are activation functions? Now you can think of activation function as a non-linear, right? Non-linear mathematical or transformation, basically mathematical function or transformation, which are applied basically to the output of the output of neuron, right? In a neural network, basically to determine the output signal. So it's applied on the output of a neuron to determine how the output signal of the neuron would look. So basically, let's say if I have this neuron where the output of neuron is just the weighted sum of the input values plus the bias, right? Now there is some input which comes into it, x1, x2, x3. There are weights w1, w2, w3. There is an output, right? There is a bias applied, right? So this is a normal neuron without an activation function. Before just the output, an activation function is applied. This is where it is applied. And why it is applied? It is done to achieve non-linearity in the output of the neuron. Let's say I have a neural network, something like this, right? Something like this. The output of this is the input layer, this is the input layer, this is the hidden layer, right? And this is the output layer, right? This is the input 1, this is input 2, this is h1, this is h2, right? Now the input layer feeds into the hidden layers. For each of the hidden layers, it feeds like this, right? And it goes to the output layer. Now let's say this is w1, this is w2, this is w3, this is w4, right? It has the hidden layer has bias 1, bias 2, this is w5, weight 5, and w6. Now these are the biases, bias 1 and bias 2. If I say what will be the output of hidden layer 1, it would be I1, or basically this is the I1 W1 plus I2 W2, right? I2 W3, right, plus B1. Similarly, for H2, it will be I1 W2 plus I2 W4 plus B2, right? And the end output of this neuron will be output. What it will be? It will be H1 W5 plus H2 W6 plus, if there, let's say end bias is there of this neuron, plus bias, right? Without any activation function, this will be a linear equation, right? This will be a linear equation. So any weighted sum or weighted bias, addition, subtraction on a linear equation gives a linear output as well, right? Until unless any non-linearity is applied on top of it. So this is where, so when before the output, an activation function is applied, which adds non-linearity to it. Why do we need non-linearity on the first hand, right? So if no activation function, is applied, so a neural network with high number of neuron and high number of layers, it will still be limited in what it can learn, right? Because the output would always be a simple linear combination of the inputs. So जो output होगा, that will just be a simple linear combination of the inputs, right? Activation function, how it helps? It helps by introducing non-linearity. It introduces non-linearity into the network. The neuron, that is the neuron. Output can be more complex. The output of the neuron, it can be more complex than a simple linear sum of its inputs. By adding basically non-linearity, network can model more complex relationships. More complex relationships can be modeled, right, between the inputs and output, allowing it to discover more number of patterns. So activation functions, basically it performs two tasks. First, it decides if a neuron should be activated, right? And basically should be activated based on the weighted sum and the bias term, based on the weighted sum and bias, right? Second, there is a concept of back propagation, which basically that is how the neural networks adjust their weights and biases, and the losses are reduced. So it helps in doing that back propagation. That is what activation function have two tasks for. One is the deciding if a neuron will be activated. Second will be back propagation help, right? It helps in back propagation. Now, what are the types of, so we understood basically why do we need activation function, how it helps, basically where it is actually applied, right? So what are the types of activation functions? Now, first is binary. It can only output 0 or 1, right? Second is linear, right? Values are based on linear equation, are based on linear equation, right? Third is non-linear. So you will hear about sigmoid, you will hear about softmax, you will hear about rectified linear units, right? These are all non-linear activation functions. These are already inbuilt in TensorFlow, right? You don't need to worry about implementing them. But now we will look on how we can implement, let's say, these activation functions on our own, within our own, right? Now, let's try to decode a few of the activation functions. We can't go through all of it, but we'll try to decode the most popular of them. First is this sigmoid activation functions. Sigmoid activation function, right? What it does is, it is used basically for binary classes. If a problem is there where we are classifying between two different things, binary, there it is used, right? It out of the two values, it gives probabilities such that the probability sum is equal to 1. So it is generally used for binary classes, and it creates a probability distribution such that the sum of all the probabilities is equal to 1, and the output is between 0 to 1, right? Now, how does the sigmoid activation function look? It looks like this. F of x, the function, is 1 plus e to the power minus x, right? This is the sigmoid activation function. We'll look at its implementation, but let's discuss few of its drawbacks. What are few of its drawbacks? So you'll hear about a term called vanishing gradient. What is it? So when input becomes, basically, let's say input becomes increasingly large or tiny, right? When input is very large or very tiny, the gradient of the functions. What are gradients? So we'll talk about it in future classes, but gradients are, you can think about it, vector of partial derivatives, right? Vector of partial derivatives, right? So what is vanishing gradient? It is one of the drawback of sigmoid activation function, and when the input is very large or very tiny, this occurs, vanishing gradient, because the gradient of the function becomes very, very small. Gradient of function becomes very small, right? So this is one of the drawback. Let's quickly implement this sigmoid activation function, basically, right, in Python, how we can do it. Although in TensorFlow, if you go into TensorFlow activation functions. So inside the keras.activations module, you'll see all these activation: 10H, Swish, Soft Sign, Soft Plus, Soft Max, ReLU, Sigmoid, Serialize, ReLU, ReLU 6. All these activation functions are already present, and we can directly call them and use them within our code. But quickly, let's implement few of it just to understand how it works, right? So what I'll do is I'll just import few libraries. Import matplotlib.pyplot splt, right? Import numpy as np, right? Import math, right? Let's say the x variable looks like this. We create few x variable, right? np.lin space, and we take certain values from -10 to 10, and how many values? 100 values, equally spaced values, right? And this z represents our sigmoid activation function, right? We do 1 divided by what we talked about, 1 plus np dot exponent, that is e raised to the power what? -x, right? This represents my sigmoid activation function. 1 plus, this will be 1 plus, right? Now if I try to run this these values against my sigmoid activation functions, let's say I'll do plt dot plot x comma z, right? And I do plt x label x, plt y label z, plt dot show. So x label is x, z is basically, this is sigmoid of x, right? And I do, let's say, just add a title, sigmoid function, right? If I run this, so this is how my sigmoid function looks, right? If you see, it lies between 0 to -1, and since we did in space from -10 to 10, this is the curve. But the thing is, it lies between 0 to 1. It creates a distribution between 0 to 1. So this is how the sigmoid activation function looks. Let's talk about another one. One of a very famous activation function is that is 10H, right? Or we also call it as hyperbolic tangent, right? So the input basically to it is any real number, right? And the output is between -1 to 1. And how this function basically looks is, f of x is e raised to power x minus e raised to power minus x divided by e raised to power x plus e raised to power minus x, right? Now the drawbacks, it also suffers from vanishing gradient, right? This is one of the biggest drawback it has. And 10H, it is mostly used in hidden layers there, right? Let's implement this as well just to see how it looks, right? Now we'll just copy paste the same code and we'll just change the function in between, right? Imported the libraries, I copied the same code. I'll just change this function z, what it is equal to. It is equal to np dot exp x minus np dot exp minus x divided by np dot exp x plus np dot exp minus x, right? We close the bracket. Now this is the sigmoid activation function, exponential of x minus exponential of minus x divided by exponential of x plus exponential of minus x, right? If I run this, let me run this again. This is tan h. I'm sorry. This will be tan h. Tan h. And this will be tan h function. H function. Right, it's the same. You might feel the curve is same between for sigmoid and this, but the only subtle difference is it lies between, the range lies between -1 to 1 in tan h, right? That's one difference. Now let's talk about another one of activation function, that is rectified linear unit. ReLU, right? It is defined as f of x, and we take it as max of 0 comma x. So whatever value we feed it in, it takes the max of 0 comma x. So basically it removes negative values, right? So it sets all negative to 0 and keeps positive as it is. So it's easy to implement and it's less memory intensive, so as to say, right? Computationally, it's efficient compared to other ones, because the computation, you see, other exponents we need to calculate, but here it's not allowing the negative values. Now it has its drawbacks, right? We see a concept of dying ReLU here. What does it mean is, it happens whenever whenever, let's say, neuron input is negative, leading to the output of that neuron being 0, right? And if it happens too frequently, then the neuron dies, right? It does not produce any output. If it happens too frequently that multiple neurons are having negative values, or that particular neuron is multiple time having negative values, the output will always be 0 for that neuron, and we say that neuron has died. So dying ReLU is one of the problem of rectified linear unit function, and so we say when it died and it had stopped learning, right? To overcome rectifying ReLU's problem, we have something called as leaky ReLU. Leaky ReLU, right? It says, and this is just max of 0.1 of x comma x. So instead of doing it 0, we take a very small fraction of that value, right? So let's implement again these both. It's again easy to implement. I'll just copy paste the same thing, right? I'll keep the same. Z is max of 0 comma x. If I linear unit, so it's basically, it should be np dot maximum, right? We do np of maximum. Now if we run this is the ReLU function, right? This is how it looks. And if I do leaky ReLU, I'll just add, for example, 0.1 x. 1 by x. This is how it looks. Like it solves the problem of dying ReLU, right? And then there is also we have exponential linear units, exponential linear units, right? And it prevents dying ReLU, prevents dying ReLU, basically, right? It looks something like this. Fx is x whenever x is greater than 0, or it will be alpha e raised to the power x minus 1 whenever x is less than 0. So alpha is a small value which we take, right? For um, you can say it kind of a learning rate which we use. There is also um, parametric ReLU, where we do it as f of x is maximum of a of x comma x. A is a slope parameter, like a is a slope parameter here, slope parameter for negative values, right? So this is certain activation functions which are very prevalent in when we work on deep learning neural networks. There is also one very famous called as softmax, right? So we talked about sigmoid, right? Sigmoid is for binary classification. It produces a probability distribution for those two values, and it sums up to 1. Now for softmax, it's like if we have n values and we pass it through softmax, it will create a probability distribution for those n values, which will sum up to 1. Sum up to 1. For example, let me quickly show an implementation of softmax to you, right? So let's say I do import numpy as np, right? And I do def softmax. I pass x values inside it. I say exponential of x equals to np.exp x minus np.max of x, right? And we do return exponential of x divided by np dot sum of exp underscore x. So what is the formula for softmax? Just let me show you. It will be easier to understand. So softmax xi is e raised to the power xi for all the values, and summation of j e raised to the power x into j. So this is what is softmax, right? For all the j values, xj. Basically, it's not j here. It is xj, right? So e raised to the power basically, if you understand from here, exponential of x minus the current value minus max of the values. So basically, we do this if we don't actually do this, right? Now this is the actual formula, the np dot exponential of x and that divided by sum of all the values of the exponential of the arrays which we pass in here. But what happens if we don't do this, right? We are doing np dot max minus x. It will cause overflow. If the integer is too long, it will cause overflow within the this function, right? To avoid it, we kind of subtract the maximum value and keep it within range to avoid overflow, right? It will give us the same answer without it as well, but just to avoid overflow, we do this. Now let's say we have certain scores, right? 2.0 comma 1.0 comma 0.1, right? We need to find the probability distribution for all of this. So by default, if you see, this is the maximum, so this will have the maximum probability, this will have the second max, and this will have the lowest probability. But how softmax works is, so probabilities are softmax scores, right? And if I do print probabilities, see, these are the probabilities. So 65% probability for this one, 24% for this one, and lowest for this one. So and if you sum all of this, let's say if I do sum of this one, Getting a comma here, right? So see, the properties come out, the sum of the properties come out to be 1. So this is what softmax does. Sigmoid basically creates a probability distribution, and it is used when there is binary classification or binary values involved, and it creates a probability distribution for those binary values such that the sum is equal to 1. Softmax, on the other hand, works for multiple categorical values. So it is involved whenever there are more, whenever, let's say, there are a lot of categories, and we want to create, let's say, there are 10 values, and we want to find the probability of the highest value, right? Or there are 10 different categories, and we want to find the probability of the highest value. So that is where we'll feed all those values within the softmax function, and it will give us out a probability distribution such that the one is the sum of those distribution is 1. So this is what softmax or 10H or sigmoid, all these activation function work on, and this is why activation function is needed. It basically, the gist is, it adds non-linearity to our model so that it can learn more complex patterns. Thank you so much. I'll be back with another episode.